All right. So here's another question. Again, it's asking for what's the shear force and bending moment as a function of x. So I didn't add that on there, but I'll go ahead and kind of pencil in where I think x is coming from, left to right. And we'll apply the same kind of strategy we did earlier. We'll have to decide how many sets of equations do we need. Well, the first thing you should notice is that the whole structure doesn't have a continuous load, and it's got this little thing here which throws it off, right? You got an overhang piece. So you're going to have to write one set of equations that are valid in this range, which is 0 to 4. And then you're going to have another set of equations which are valid from 4 to 20. Don't worry about this section A. This problem was originally asking what is the shear moment at section A. We're not doing that. We're writing an equation. So again, I'm going to make a cut somewhere in that first 4 feet. I'm going to decide, hey, do I work the left side or I work the right side? Again, I think there's a clear choice here. You definitely want to work the left side. Now, when you get out here between 4 and 20, now you're saying, do I want to work the left side or the right side? I'm not sure which would be the best. If you look at the left side, you're going to have to find a reaction and deal with all these pieces. And this will be a function of x. And work on the right-hand side, you still have to find a reaction and the concentrated equivalent of this piece, and it will also be a function of x. So I think I'll go right on that one. There's no wrong choice. There's just a choice that presents you less of a challenge sometimes. And I think the first one, this will be less challenging than the right-hand side. Here, I don't see really anything to help out. But looking ahead, if I do work the right-hand side here, I'll need my reaction at C. So the first thing I need to do is draw a quick free body diagram of the whole structure and find those reactions. So I'll start by drawing the beam, and I'll assume I have a reaction at BY and CY. And then I know out here at the very end I have an 8 kip force. That's 4 feet. And then I'll need the concentrated equivalent of this section. So it's a rectangle. Area of a rectangle is base times height, so that's 16 times 2, so that's going to be a concentrated equivalent force of 32. And it's going to happen right in the middle. So halfway of 16 is 8, so that would be 8 feet and 8 feet. So I have enough now to find my reactions. And the reaction I'm interested in is CY. So what's the best way to get CY? We will sum moments where? At B. So summing moments at B, I'll start with my 8 kip force. Does that create positive moment about B or negative moment about B? Positive. So that'll be an 8 kip force times a 4-foot moment arm. Then I'm looking at the concentrated equivalent 32 kip force about B, positive or negative moment? Negative. And that'll have a moment arm of 8 feet. And then CY, the way I've assumed it, creates what kind of moment about B, positive or negative? Positive. That'll be CY and have a moment arm of 16. So what's CY equal to? 14? Anybody else get 14? 14, 2 14s? You get 3 14s? Going once, twice. All right, sold for 14. $14 kips acting up. Does that make sense? How come it's not half? Why is it not 16? Because this little guy over here is trying to push down, which is kind of help lifting it up a little bit. It's taking a little bit of the load off. So that seems reasonable. Okay, so let's plow ahead. So I'm going to start with, I'm going to work from left to right. So I'm going to work this side, and I'm going to work the left side. So this equation will be valid between 0 and 4. And my free body diagram looks like this. Fortunately, the whole thing is just of length x, and I have at the very end the 8 kip load, and then at the cut face I'll assume positive shear force and positive bending moment.
Are there any rules for determining the positive or negative of your shear force and moment? Do you always want them to be positive?
Well, you know, I always, when I do these problems, I always assume the positive values for shear force and bending moment. It's easier for me, I think, and I think for you too. When you do your calculations and you get negatives, then you can immediately think, I've got a negative bending moment, which means something. Or I've got a negative shear force. That doesn't mean so much. And I would encourage you to, I've said this more than once, I want to say it again. I would encourage you not to go back to your free body diagram when you get a negative value and start trying to flip the arrows around. That's just a recipe for disaster on the exam. Because you'll confuse you, and then you'll confuse me, and, you know, the red pen will come out, and it just doesn't usually work out. So even if you don't like this, whatever assumption you choose, that's fine. Just stick with it. But when you're done, you have to know the difference between a positive bending moment and a negative bending moment. So I think it's easier just to start off with a positive bending moment and just let it be. Now on these reaction forces, I just guess up. These are not shear forces, by the way. And later in the course, later today and tomorrow, we'll start going back and we'll start assuming shear forces here, which have sign conventions. So we'll talk about that. But right now, these are just forces, and they're good enough. So what we'll do here is we're going to solve for the moment by summing moments at the cut. We've done that a few times. And looking at my free body diagram, the positive bending moment I assume is what kind of moment when I do my statics with right-hand rule. This one is positive. What kind of moment does the 8 kip force create about the cut surface? Positive. And the moment is the force 8 kips times the moment arm x. That's it. So I'll solve for the moment. The moment is minus 8x, and that will have units of kip feet. Can I check that moment anywhere in this 0 to 4 foot range? What's the moment of the free end? 0. So if I put in x equals 0, I should get 0. And hey, it works. So I do know that the moment at x equals 0 should be 0, and my equation gives me that, so I'm feeling pretty good about that part of it. Next, I can sum forces in the y direction, make sure my free body is in equilibrium. And when I do that, what do I have? Well, my shear force, this is a positive shear force, but when I'm summing forces, I assume up is positive. So that force is down. My 8 kip force is down. So when I solve for the shear, I get minus 8 kips, constant force. And you can quickly check that the derivative of your moment, is it equal to the shear? The answer is yes. So I got 2 good things there going on. I'm feeling pretty good now about these. I think these are in good shape. And what's a little weird to think about is that I have a constant shear. So what's the shear at the very end? It's negative 8. And it's really because of that 8 kip force there. So what's next? Now I'm going to pick this cut somewhere between 4 and, what's the total length? 20. So I'm going to pick that range, and in that range I'm going to work the right hand side. So let's draw that free body diagram. So there's my beam. So the distance to the cut is x, so the remaining segment of my free body diagram is what? The total length minus x. The total length is 20. That's kind of unusual. Don't get the feeling that our beams are all 20 feet long. The last couple of problems have all been 20. That's just unfortunate coincidence, yeah. And what do I have on that side? Well, I've got my C reaction, which I've already found. It was up and equal to 14 kips. I've got the distributed load, which has an intensity of 2 kips per foot. I'm going to turn that into a concentrated equivalent. We'll do that in a second. It'll have a value of F, and the distance to the centroid from the cut I'll call D. We'll calculate those in just a second. And then on my cut face, I'm going to assume positive bending moment and positive shear force. Which direction is positive shear force, up or down? It's going to be up. It's 50-50. Why is it up? Because it would make the beam rotate in which direction? Clockwise. Anytime you make the beam rotate clockwise, that's a positive shear force. Even if you look at this one over here, which way is it going to rotate? Clockwise. Now to make this little guy smile, this is the direction I'd have to apply my positive bending moment. So before we get started, what is this force F? Well, it's a rectangle. It's going to be base, which is 20 minus x, times height, which is 2. And what's the distance going to be to the centroid of that rectangle that has a base dimension of 20 minus x?
20 minus x divided by 2.
It'll just be half of that, right? So there's a 20 minus x over 2. And I'll just leave those alone right now, see what the equation gives me. So now if I come back and I sum moments at the cut, again, make sure it's in equilibrium. So this is my statics equation. It has a different sign convention. So looking at this free body, I'll start from the left and work to the right. What kind of moment does this create using right-hand rule? Negative. The force F about the cut creates positive or negative moment? Also negative. So the force is going to be 2 times 20 minus x, and the distance is going to be 20 minus x over 2. And then I've got this 14 kip force sitting way out here. What kind of moment does it create about the cut? Positive or negative? Positive. So that'll have a value of 14 kips and a moment arm of 20 minus x. So I'm solving for my moment. So my moment is going to be equal to, just pull it to the other side of the equation. I got all that. So this 2 cancels that 2. And I end up with negative 20 minus x squared. And then you can multiply that or just leave it. I think I'll just leave it. 14 times 20 minus x. And that should have the units of kip feet. Does that work? Well, looking at this range between B and C, do I know the moment anywhere? What's the moment at C? It's 0. It's a pin, right? So is the moment at x equal 20 equal to 0 from this equation?
Yes.
The answer is yes. You put an x equal 20 and x equal 20, you get 0. So that seems to work. What else should work? Well, this equation and that equation share a point. What point did they share? 4. What is the moment at x equal 4? Negative 30. What is the moment here at x equal 4? That takes a little harder, it's a little bit more to get to. I bet it's going to be negative 32. But you could check that. So if you really have the extra time, you would say, I'll call this moment 1 and moment 2. Moment 1 at x equal 4 should equal moment 2 at x equal 4. And while you ponder that, I'll go ahead and check my shear. I can do that by summing forces in the y direction. I'll assume up, it's positive. So looking at my free body diagram, my shear is up, so that's positive. My force is down, so that's negative. And the force was 2 times 20 minus x. And what else do I have? Oh, this 14 is up. So if I solve for my shear, what do I get? Everything goes to the other side of the equation. I get 2 times 20 minus x minus 14. And that should be the shear with units of kips. One more thing we can check. If you take the derivative of the moment, do you get the shear? You do. Check. Anybody actually do that calculation right there? Do you get, when you put in 4 here, do you get negative 32? Anybody do that? Nobody's playing along at home?
When you put in 4 for x or for the whole equation?
We'll evaluate this equation at x equal 4. So this would be 16 squared negative, and this would be 14 times 16 positive. I think it's 32. That's 2 extra 6. Hey! I'll put my little green check there too. I like to have my green checks. So all is good. What if I then ask you, what is the variation of shear force and bending moment along the beam? Could you graph these things? You could graph this function over the first 4 feet and then graph this function over the next, and you could have a continuous plot of shear and moment. And you could probably then locate where the maximum moment was. When you try to maximize a function, what do? You take the derivative. Have we been taking any derivatives lately? The shear. So where the shear is 0, the moment is usually maximum or minimum. So I could actually solve for where the shear is 0, plug that value back in and get my maximum value. We haven't done that before. That's exciting. So now you can design a beam because you could calculate for a given load combination what the maximum moment is. And if you know the maximum moment, then if you actually look back into the freshman class, you could design a reinforced concrete beam because you now know the maximum moment you have to account for. So you can pick the size, how wide it is, how deep it is, how much rebar. You could come up with a beam that would have that moment capacity. And you have designed a reinforced concrete beam. Yee-hoo! You can applaud. Or not. Well, that was like a golf clap.